by proposing a very simple model for choice probability, and then testing some prediction of this model back in the original data set of Britton et al. 1996. So I think I can almost skip all my introduction, but just start by mentioning my collaborators, Albert Comte, Jaime de la Rocha, Alfonso Renard, Alex Roxin, that are all here today. And I'd also like to thank Ken Britton, Tony Mofshon, Bill Newsom, Mike Shadlin, and Ehud Suhari, which did these experiments back in the 90s. And what is very important for my work and also for others is that they provided this data on a web platform maintained by Wyeth Bear, so that everyone can use this data. So this is like a very rare example of data sharing, which already happened a long time ago. Okay, so what I'm trying to study is the very basic random dot motion task, and I will focus exclusively on the zero coherence stimulus. So we have already seen today that the behavioral responses are variable on one hand, and also the neural responses are variable, and then in this landmark paper, 1996, there was this idea, well, to combine this and to introduce choice probability as a measure of the relationship between those two forms of variability. And yeah, Bruce just showed the model proposed by Mike Shadlin that accounts for, or that explains in an elegant way how the variability in two pools of sensory neurons finally impacts decision. And it was also mentioned that correlations are important in this model to get choice probabilities different from 0.5. So what Bruce just mentioned in the discussion now was that there is something that this model does not explain, is the timing of choice probabilities. In order to illustrate that, I'll first show psychophysical kernels. One of them, so this one here measured in a different experiments, in a disparity discrimination experiment by Ni and Cumming. And this here shows motion energy for right versus left choices, which is also something like the psychophysical kernel. What both of those have in common is that they decay over time. And this is, to simplify things a bit, I introduce here this term decision window, which you will see in many of the slides that come. So here it's, the important fact is that the decay. Here it seems really to be like a window which is important for the decision. So what this means in the end is that fluctuations in the stimulus that you present to the subject just have an impact on the decision early in the trial, in fixed duration experiments. So this would mean, as a consequence, that if choice probability reflects this causal impact of fluctuations in the stimulus or fluctuations intrinsic fluctuations in the sensory neurons, then basically it should have the same time course, right? However, if we look at the time course of choice probabilities across many experiments, what we typically see is that choice probability is sustained over time. So there's just one study which did in the same animal. So this is again the decision window, just to illustrate that there's a mismatch between these two findings. So there's one study which by Ni and Cumming where actually the psychophysical kernels and choice probabilities were characterized in the same experiments, and you can clearly see that there's a mismatch between these two. So the first question that I'm interested in is why is choice probability sustained if decisions rely mostly on early sensory evidence? So the second important question is what is the origin of correlated variability, and which is also not answered in the original model. So correlations are necessary, but it's still unclear where they come from. So one prominent hypothesis is that, well, correlations are just intrinsically generated, for example, in area MT, perhaps by anatomically shared inputs, or it could also be to the structure in the network. So, for example, through slow oscillations or competition between different neurons. Other sources of variability, of shared variability, would be bottom-up effects. So the very, like the very stimulus itself, which might introduce correlations, or fluctuations in previous processing stages. And the last one is top-down effects, which Bruce has been talking about already extensively. So this is the second question. What is the impact and the contribution of these different sources of correlations on choice probability? And yeah, as I said, what we do is we develop a simple model which just consists of two pools of neurons. And let me start with the decision circuit. So for the decision circuit, we use basically the model proposed by Chao Ching Wang, 2002, consisting of two populations of neurons that have a winner-take-all dynamics. And yeah, this is the network that actually makes the decision. And we couple it to a network of a similar architecture, which represents the sensory circuits, and which also has two populations of neurons. So that the big difference between the two circuits is that this one here has winner-take-all dynamics, so there's strong competition between these two pools, giving rise to the decision, whereas the sensory network is in a linear regime. So there's just a weak competition between those two pools, and this represents the so this network represents the stimulus. So what we do in order to study the different sources of correlations is we dissect the model. So what we do is we have on the one end we have bottom-up contributions, which in our case is just fluctuations in the stimulus. Then we have intrinsic sources of correlations, which are due to shared input. So shared external input from a population of Poisson neurons on the one hand, and also shared recurrent input. And then we have top-down feedback signals. So the top-down feedback signals in our case is a very simple feedback signal. It's just a decision taken here, fed back to the sensory circuit. So I start with looking at the impact of the intrinsic fluctuations, and to exclusively focus on that, we actually use a constant stimulus as an input. So there's no fluctuations in the stimulus, and there's no top-down signals. So if you run a simulation of this network, then we get activity so when the stimulus comes on, we get an increase in activity in the two sensory populations. The inputs are the same for both, so also the firing rate is very similar in these two. And in the decision circuit, we see that slowly there's a decision being made. Okay. So now if we repeat many of those trials, we can calculate choice probabilities, and we can calculate correlations. So and what we see is that correlations in the sensory circuit, and I'm focusing all the time on the sensory circuit. So correlations in the sensory circuit are very low on average. And choice probabilities are basically at chance level at 0.5. And there's no, if we condition the responses of the sensory circuit on the decision, so we look at preferred choice and non-preferred choice trials and calculate the average, then we don't see any difference here. So why is this the case? So the sensory network is operating in an asynchronous mode. So it's a balanced network, and even if there's a large fraction of shared inputs, this network does not generate strong correlations. So this is very similar to what has been described by Renard et al., even if there's some competition, so, and it's true if there's not very strong competition in the sensory circuit. The next thing we're going to analyze is what happens if there's fluctuations in the stimulus. So this is again a single trial. So now the stimulus is fluctuating in time. And this leads to also fluctuating population activity in the sensory circuit. And now, and again in the decision circuit, you see the decision being made. Now we can look at a specific instance in time. For example, here, where you see a strong fluctuation let's say, towards leftward motion. So the right line is above the blue one here. And you see that there's also a fluctuation in the sensory activity. And it seems almost that the decision is really influenced at this point in time, right? This is where the population 1 increases the rate. However, later during the trial, a strong fluctuations in the opposite direction does have an effect on the sensory population, but it is not strong enough to really change the decision which has already been taken. So another way to look at this is looking at the dynamics of the decision circuit here in terms of an energy landscape, where when the network has made the decision, it has reached one of the attractors, and it's very difficult for fluctuation to bring it back to the other well here. So now we have a situation where the stimulus that is different for pool 1 and pool 2 creates correlations. So now we have positive and negative correlations between the pools of sensory neurons. We get choice probability, which rises fast and then decays over time. And basically the reason for this is that only the fluctuations early in the trial impact the decision. And yeah, that's it basically. So trial-to-trial stimulus fluctuations generate spurious correlations and causal choice probability. So now, what about the top-down signal? So this simple top-down feedback signal, just feeding back the decision to the sensory circuit, what does it do? If we look at the choice-conditioned average firing rates in the sensory circuit, we see that they diverge over time, just as the rates in the decision circuit do, right? This again introduces correlations that now grow over time and create choice probability that is also increasing over time. So this is now what we call an acausal choice probability. So it's just reflecting the decision. It's not that the variability that we see in the sensory circuit, it's not impacting the decision, it's reflecting the decision. Put both things at the same time, so stimulus fluctuations and the top-down signal. And if we do that, we can get sustained choice probability, just as found in many experiments. We can also calculate the psychophysical kernel when we just have stimulus fluctuations, or when we have stimulus fluctuations and the top-down signal. And what we get looks basically very similar to the data that Nienburg and Cumming observed. So psychophysical kernel reflects or mirrors basically the causal part of choice probability. And yeah. So now one thing is that, or one additional thing is that now I can change the dynamics of my circuit and just make the decision faster or slower. So I show here just an example where the decision dynamics is slower. So now now stimuli like occurring at time point 1 second still have an impact on the decision. But this will also lead to a slower build-up of the top-down signal that is reflecting the decision. So in the end, we can get, again, choice probability that is sustained. So this is quite, in the simple model, this is quite a robust effect, because we have the underlying thing here is just one time scale, right? It's the time scale of the decision. So now that we have that model, we want to make very specific predictions and test them in the original data set. So the first one is, well, stimulus fluctuations should have an impact on the neural responses in MT. Of course, we are not the first one to observe that or to propose that, so it has been shown in this very famous rastergram that when you stimulate a single MT neuron with the same stimulus in each tile. So what we have on the axis here is tiles, and this is time. So we present the same stimulus in each tile, which I call the replicate stimulus condition. Then this raster plot is very different from the stochastic stimulus condition, where a different stimulus is used in each trial. So what's typically done in the experiments is this situation. So you present a different realization of the stimulus each time, and this is a kind of control condition. So we wondered whether, what is actually the impact of this, okay? So the first thing we want to look at is on neural variability and covariability in these two conditions. So now we are looking at the variability not of the PSDH in time, but of the variability across trials. In order to do that, we calculate the Fano factor. So and this is the Fano factor here calculated in 250 millisecond windows. And what we see is that in the replicate stimulus condition, there's a remarkable drop in the Fano factor. So meaning, yeah, the difference would be like the impact of the stimulus, so of the spurious variability caused by the stimulus. And this is a very significant effect. We can do the same thing for pairwise correlations, and I have to note that this is just data for one pair. So in the data set, there are two pairs, and the other pair has a very similar behavior, but this is just one pair. And we can do this depending on, so for different time windows, and yeah, it's a very robust effect. So the next prediction is if there's really an impact of the stimulus fluctuations, then it should be as I just showed you in the model. So if you have now, stimulus and top-down co-fluctuations, we should see sustained choice probability. But in the replicate stimulus condition, where the stimulus fluctuations are the temporal fluctuations in the stimulus are the same in each trial, but there's no fluctuation from trial to trial. So the early component of choice probability should basically be reduced in this condition. And this is also what we see in the data here. So this again is for a specific window of 215 milliseconds. The important thing of this prediction is that choice probabilities for early and for late, the choice probabilities for stochastic versus replicate should be different, but they should only be different early in the trial. So in the causal part of the choice probability. However, late in the trial, where the decision, so where the top-down feedback signal dominates choice probability, there should be no difference. And this is exactly what we find. And this is again for different window sizes. So choice probabilities decrease for the replicate stimulus early in the trial, but not late. So prediction 3 will be again about the stimulus fluctuations, and then I go to predictions related to the top-down signal. And this prediction, yeah, I have to introduce first the double pass method used in psychophysics. Basically, what the double pass method is about, well, it's a very simple idea where you repeat one stimulus. So you have a stimulus sequence, and you repeat each stimulus twice. Okay? And then you have the stimulus, you have your decisions, left choice, right choice. And basically what you can use this is for determining the consistency of the subject, right? So how, if you present stimulus 2 times and you get the same choice for both of them, then this would be a consistent behavior. So in this case, I have the stimulus A has 2 right choices. So this is what I call a consistent stimulus. And stimulus B, which is also repeated here, leads to a right choice and to a left choice. So this is an inconsistent stimulus. So now if one calculated a psychophysical kernel, but now separating the stimuli depending on whether they are consistent or inconsistent stimuli, you get the following thing. So the inconsistent stimuli have a flat psychophysical kernel. Why is this the case? Well, the psychophysical kernel is the average stimulus that led to one choice. Okay. So now if a stimulus participates in left choices but also in the right choices, then its effect just averages out and it gives you 0. So this means, on the other hand, immediately that if you take now the consistent so the set of consistent stimuli, it must give you some psychophysical kernel with a higher amplitude, just because the average of those two should give you again the psychophysical kernel when using all the tiles. Okay, so actually you see that this is not well, it's the average, but you have to weigh the average with the consistency of the subject. And in the simulation that I did here, the consistency is about 70%. So so there are more stimuli that are consistent than stimuli that are inconsistent. Okay. So now, if you use this simple manipulation in an experiment, and this is something that has not yet been tested, then we should again see the effect on choice probability. So, and the prediction that the model makes is that the inconsistent stimuli basically are very similar, give a very similar result to what we to the replicate stimulus condition. So we should see a reduction in choice probability early in the trial, and the same should hold for the correlations. And consistent stimuli should increase choice probability in the same time window. And again, the weighted average of the two should give you the choice probability you measure when you do not do this manipulation. So this is something that still has to be tested.
Sorry, maybe I'm blanking out, but why are you doing this difference between consistent and inconsistent?
Yeah.
The result has to mathematically look like that. It has to look like that. So it's not a testable prediction. Whatever the results are, the curve for consistent, just like you explained, it has to be higher than for
the psychophysical kernel, yes. So this is a mathematical thing. This can't be, but here it shows. I mean, here this is just true if you really see if really the early part of choice probability is actually caused by the fluctuations in the stimulus, right?
Oh, right, because we're
But it could be another.
Right, okay, fine.
It could be due to some other source, and then you wouldn't see it.
Okay.
So this, if you don't see that, then something is wrong. Yeah. Yeah. Okay. So prediction 4 is about correlations. So about choice condition correlations. So again, we are separating tiles depending on the choice, and we calculate then the correlations just for preferred choices or for non-preferred choices. And the prediction of the model is that, well, if there's a top-down signal, so like this combination of bottom-up and top-down signal, basically we should see a decrease in the correlations throughout the tile. If there's just an early component, then we should see the decrease there. Just a few words why we expect this first one. So if you have a causal impact of the variability of neurons on the choice, then what we get is if you have a response of neuron 1, response of neuron 2, so let's assume we have just 2 neurons, basically the decision boundary would be, and we consider the sum of the two, then the decision boundary would look like this, and now if I separate the tiles depending on the choice, so I would have this and this, then I get smaller correlations, just because of the separation that I do here, okay? So whereas the overall correlations were here 0.5. Now if I do this separation, I will get 2 lower values. So this is now what, if I do this in the model, then if I have just I've only now bottom-up correlations biasing the decision, then I would see the difference here. And if I have both causal and top-down correlations, then I would see it throughout. And yeah, if you look in the if we do this in the experimental data from Zuhari, and this is for 38, so the average of 38 pairs, then it's not actually what we see. So what we see is we see a decrease for preferred choices, but we don't see the decrease for the non-preferred choices. So I'll go a bit quickly over that. We can talk later about what we think could be the reason for that. So we see a decrease for preferred choices, but not for the non-preferred choices. Okay, so the last prediction concerns now the heterogeneity of single neurons. So once we believe that there is a top-down, so yeah.
So the correlations do you expect to decrease in the late phase, not in the early phase?
Exactly. So what?
Decrease in the both phases?
Yeah, actually, so there is a trend. If you look at the preferred choices, right? You see that overall we see a decrease if we do the choice conditioning, and it's there early and late, but it's a trend. So it's yeah, actually this this difference here is not significant, given the data that we have.
But you wouldn't expect that from the model, no?
We would expect, oh yeah, so the model prediction would be that we see the difference throughout. Yeah. So the last prediction concerns the heterogeneity of neurons. So once we believe that there is an early and a late component of choice probability, then yeah, there is no reason to believe that all the neurons show exactly the same time course, right? So there might be neurons that are more afferently driven, so they show more the effect of the stimulus, and the other neurons that receive more the top-down signal, or just show more kind of this effect. So again, if you look at this heterogeneity in the data, then it should reflect contributions of these two sources. So now in the model, this is something very easy to do. So I can get an average choice, sustained choice probability with very heterogeneous single neuron responses. So actually what I do in the neuron is just getting rid of the feedback signal or changing the afferent strength and the feedback strength of individual neurons, and then I get these very different time courses. So if you look at in the experimental data, then there also seems to be quite a large variability of single neurons choice probability. So of course this is very noisy, and now we thought about a way how to quantify this somehow has something to do with what I propose here. It's just noisy single neuron choice probabilities. Okay, so the idea is that if choice probabilities of individual neurons are a bit noisy, but they are consistent, so each neuron has a different value of choice. So this is like time course of 3 different neurons, having different values of choice probabilities, but they are all sustained. So now, if I take 2 specific points in time and I calculate the correlation between, and then each neuron is 1 point, and I calculate the correlation between all the neurons, then we'll get a very high correlation. And if I do this for different points in time, then I will get something that there's nothing to be seen, so it's just black. Don't worry. So then I get something that is just an overall flat correlation matrix. So be careful about that, because this looks somehow very similar to what Mike Shadlin showed in the core CE plot. But the difference is here, I look across different neurons. So this is not across. So we share the thing that we look at different points in time, but I have different neurons here and not different trials. So it's something different, and it's it's the choice probability of single neurons. Okay, so the other extreme would be that choice probabilities of individual neurons are stochastic, and there is some correlation time, but they're just completely random. So what I get then would be a CP correlation matrix that has that shows a diagonal, right? So there's some temporal correlation here, but there's no difference between the early and late in the time. So it's just uniform. So now if I take my model that incorporates the bottom-up and the top-down contribution to choice probability, then I get something like that. So I get